again, everybody, for joining us today. So we're going to go through a webinar here, and this is on the impacts of storm drainage design standards, specifically municipal standards on sanitary system capacity. And so we've identified what we think is a pretty common and pervasive problem. So this is a new approach, and hopefully this is something that everybody can identify and realize and sort of learn from. So again, today's a good opportunity to hopefully get some value, and hopefully we can make it very educational for everybody in the group. Just wanted to say, we really do appreciate you coming out. I know we're getting up against it in terms of holidays and year-end stuff. So there's a lot of stuff going on in a lot of people's lives, and really appreciate you taking some time today. And hopefully this is our last webinar before the end of the year. So just want to wish everybody a happy holiday, and hopefully everybody can travel and see family and friends and have a nice and safe and healthy holiday season. Just a few housekeeping items. So this will be a presentation followed by sort of a Q&A session. But throughout the presentation, we've put some slide numbers in the bottom right. So if you do have any questions along the way, feel free to open up the little chat box or Q&A box at the bottom and type them in. Just refer to whichever slide number if you have a question specific to a specific slide, and we can go back and address those at the end. And then just finally, we do have some polls throughout the webinar. So as we go through, you'll see some polls pop up. So feel free to engage with those. And a lot of it's to learn a little bit more about yourselves. So with that being said, we can kind of jump right in. So just today, we'll talk a little bit about what we found, and to sort of set the stage, I'll do a quick introduction and background as to some of the problems that a lot of municipalities are facing these days in terms of wet weather flow, or I&I. We'll talk a little bit about municipal drainage standards and some of the sort of impacts that we see, and sort of the conflict that's been identified that we've noticed in these drainage standards. We'll talk about those impacts to specifically the sanitary sewer system. We'll go a little bit more into detail on some of the variables and some of the things that have to be taken into consideration when we talk about these impacts on the sanitary sewer system. We'll go into some conclusions, and then what are our recommendations, what are our next steps, and follow that with a Q&A at the end. Hopefully we can leave enough time so that if there are questions, we can leave enough time to answer those. But outside of that, if there are any questions, if you do want to engage or speak with myself or Ed, we're more than happy to work with you one-on-one or have a further conversation offline if that's something that you'd like to do. So just a quick, again, intro about Civica and who we are. So we're a company that's focused really on water, wastewater, and stormwater systems. So we help a lot of our clients manage capacity in their particularly in their collection systems. So we do a majority of our work in wastewater and stormwater systems. And our goal is really to help municipalities and communities grow during this period of rapid growth and through this changing climate that we're going through. And really our focus has been to maximize the use of existing drainage infrastructure, trying to squeeze as much out of that infrastructure that's very costly to install and maintain, and try and get the most out of the systems that we've already put into the ground. And so we have a number of services that you can see on the side that we do and we've worked on over the last 5-10 years to help municipalities achieve these goals. So a little bit about myself. So my name is Matt Malone. I'm the leader of our business development group at Civica. So I've been involved with quite a few wet weather flow reduction projects, I&I projects, flow monitoring, anything to do with sort of capacity of a wastewater or stormwater system modeling and whatnot. So I've been with Civica. I started at Civica in 2015. I did a brief stint. I went and worked at the region of Peel for a year, helping with some of their I&I reduction strategy. And then I came back to Civica in October of last year. So I have a little bit of the consulting side, but also some municipal experience as well. So I'll pass it over to Ed, maybe if you want to do a quick intro for yourself, Ed.
Thanks, Matt. My name is Edward, or Ed Graham. I've been doing this for many years now. I have graduated in '88. I'll date myself. All this time, I've basically been working in stormwater and sewage system capacity management, and that's what Civica does. We partner with municipalities. We partner with other consultants. Those are our primary relationships. Sometimes we work with developers who are working with other consultants to help them find capacities in systems, but in cooperation with the municipalities themselves. So we love to work with partners through partnerships, and we love to share a lot of the knowledge that we gain by doing R&D. We do equipment R&D, we do methods R&D, we do a lot of software R&D. So we love to share it. We love to expand the good things that we've discovered, and this is what we're doing now, and we will continue to do this through other webinars. So we love to get to know you. So Matt will talk a little bit more about that as well. But yeah, any questions, like Matt said, we can stay beyond 2 o'clock as much as you need us, and if at any other time you need us as well, you can contact us as well through our website and directly to me or to Matt or anybody else that you meet in our company as well.
Awesome. Thanks, Ed. So we'll launch our first poll, and it's always nice to kind of see who's in the audience and who's making up the attendees today. So you should see a poll pop up on your screen. So if you can just quickly answer that, we'll give everybody a couple sentences or sorry, a couple seconds to fill that out. Awesome. Okay, so it looks like we're getting majority of the answers in. So I'd say we have around, let's say 60% are municipal folks, 30 engineering, consulting, or contracting, and then another small percent that are other. So, okay. So it's a good mix, and I think this is a very good audience for the topic that we have today. So hopefully, again, there's some good educational value, and if we can have a discussion at the end, I think that'll be very meaningful as well. So again, just to talk a little bit about the objective for today, and really we want to introduce what we've identified as a problem, and this is this conflict in the design standards and how it affects sanitary sewer capacity. And really, we want to sort of get everybody up to the same speed about, introducing this problem and going through some of the methods and analysis that we did, again, just to get everybody up on the same page. And then we are doing some future webinars and one-on-one training as well, where we go more into, okay, now that we've identified this problem, what are some of the solutions that we can look at to help sort of alleviate some of these issues. And so keep an eye out for that. We will be sending out our regular newsletter and ways for you to engage with us to learn more about those upcoming webinars and training. So again, just a bit of background, and I know probably many of you are familiar with some of these concepts and ideas, but I do want to kind of set the stage for some of the stuff that Ed's going to be talking about. So the first thing is inflow and infiltration. So again, just briefly, the wastewater system or sanitary sewers are typically designed to collect wastewater, right? So it's collecting sewage from, domestic use, commercial use, industrial use, and some I&I. So there's typically some allowance for rain and snowmelt to get into the sewer system. And so in the top graphic, we show, this is a typical sort of pipe cross section. So the sewage amount is there on the bottom, and then we do allow for some I&I to get into the sewer system. And in actuality, we see in a lot of cases the situation on the right. which is there's a lot more I&I that's getting into the system than what was originally designed for. And in this particular case, there's not really an issue. The pipe's not over capacity. There's still room. So it's not causing any problems. But when we do see excess of I&I getting into the system, that's when you run into these situations like in the bottom figure where the sewer system becomes over capacity. It causes things like flooding in people's basements or spills to the environment. And that's really a big trigger for a lot of the work that we do. And so when we talk about those drivers, those triggers for I&I reduction, we're really looking at a number of different things, whether that's reducing basement flooding, trying to protect the environment by reducing, combined sewer overflows or sanitary sewer overflows or bypassing at treatment plants. There are some regulatory compliances that we're trying to follow in a lot of situations. There's also the other side of it of trying to upgrade our infrastructure. So trying to put bigger pipes or bigger pumping stations or treatment plants in the ground to accommodate these flows, which are very costly to do those things. And then there's also the impact of limiting development. If that I&I or that wet weather flow getting into the sewer is taking up that capacity, it limits the amount of new development you can put into that pipe upstream or downstream. So these are the key drivers that we see for doing I&I or wet weather flow reduction. And so what we wanted to do was to kind of poll the audience here again and see, these are sort of the drivers of creating and alleviating sanitary system capacity. So we wanted to kind of reach out to you and see which one of these is the highest priority for you, kind of knowing they're not necessarily exclusive. A lot of the programs and the things that you're working on are to help alleviate multiple of these issues. But we did want to see which one was sort of the key driver from your where you sit, as part of your priorities in your job. Which one of these is sort of most important to you from sort of most to least important? So hopefully you can see the poll launched, and if you can kind of quickly identify which one of these in order from highest importance to lowest importance, what's kind of driving I&I or wet weather flow reduction from your standpoint? Okay. So we'll just give, this one's a little more, got to do a little more work on your end. So we'll give a few extra seconds for this one. All right. Okay, so we'll probably tie it up right about there. So basically the top three we'll say are to support new growth is a big one as a top priority. B is another big one, so that would be eliminate basement flooding. And what's the next highest one? Probably A or D. So regulatory compliance or avoiding pumping station and treatment plant upgrades. So it's a very interesting, it's a very mixed result, but you can see some of the common ones. The two key common ones are to support growth and eliminate basement flooding, I would say, are two of the key ones that we've identified here, which is not surprising considering the amount of growth that's happening in Southern Ontario, but also the fact that we want to reduce and eliminate basement flooding. It's a big driver for a lot of municipalities these days. So very good. With that, I'll pass it over to Ed, and he'll take us through the next few slides.
Thanks, Matt. So what I want to start is by just giving you some facts about current drainage standards, those elements that seem to affect seem to affect the capacity of the sanitary sewers. what you're going to hear today actually benefits both systems, the storm drainage systems, as well as the sanitary capacity system as well. But it's an interesting connection between both systems. I would say it's interesting, yet it's unfortunate because we've been doing this for a long time, and not until now we're discovering that this is what's happening, and we've been trying to point fingers at different causes of system failures, and we've been spending money, a lot of money in upgrades when maybe we should have been looking at some of these issues before. The good news is that, yeah, now that we understand how these systems interact, solutions to existing problems or future problems can be significantly, I'm going to say significantly improved as compared to what we've been facing all along, which is typically let's make the system bigger. Let's replace this pipe with a bigger pipe. And as soon as we do that, let's make the pumping station downstream bigger. And let's make the treatment plant bigger. And for new development, yeah, we have to stop new development because there's no capacity in the system until we upgrade all this infrastructure that costs a lot of money, a lot of delays, and it's really not needed. There's other impacts of increasing infrastructure with respect to operation and maintaining it, as well as treating electricity, energy usage. You are sizing systems for events that are carrying water that should never be in the system in the first place. So some of the facts, I'm just going to go through this list, yeah, and then we're going to expand a little bit more as well. So the first point is that the provincial and municipal standards use the streets as the overland flow channels during large storms. We actually create rivers where the streets are. We want to do that because we want to be able to carry all that rainfall runoff, not necessarily on the storm sewers. Storm sewers are very costly to construct and to maintain in the long term, and you would need huge pipes to be able to carry up to the 100-year storm, which is the practice in North America and in Europe as well. We tend to go up to the 100-year storm, and we cannot size storm sewers for the 100-year storm in most cases. In some cases we do, wherever there's no overland flow outlet, we capture a 100-year storm, and we, from that point onward until there's a safe outlet, we size the system, underground system, for 100-year or more in some cases. Now some conservation authorities are going up to the regional for some ponds, and then the flows have to be conveyed as well. Doesn't mean that the flow rate is always bigger for the regional storm in Ontario, but sometimes it is. Depends on the size of the area. Another fact is that we get inlet blockages in the storm drainage system, and you probably, most of you, if you are involved in urban drainage in some measure, you've seen catch basins partially covered or fully covered in either debris or ice and snow. And this is a huge driver for keeping water at the surface when we don't necessarily want to keep it at the surface. The storm sewers, it used to be called the convenience system, because we want to get rid of that frequent storm water that sits on the surface or flows on the surface, because it can be a hazard, a traffic hazard. You can hydroplane, you can do all kinds of issues with water under, and it could freeze as well when you get freeze thaw. We want to get rid of that water, but inlet blockage has a very significant consequence on the sanitary sewer capacity as well, and you can see a little bit in this webinar. Inlet blockage, I know it's been cited as an operational issue. It is. It's something that we have to maintain. We have to clear the grates. But at the same time, maybe we could improve upon the design to oversize the grates or allow bigger debris to get in if the system downstream can allow the conveyance and eventually disposal into receiving waters. The third point, is that sanitary sewers and the maintenance holes are, most of them, I know that there's easements, there's other locations, parking lots, etc., that have sewers and manholes. But the point is that a lot of these sanitary and storm sewers are located in the same general areas. So whatever you're doing with the storm water, if there's any open connection into the sanitary, you will get inflows into the sanitary sewer system. Sorry, into the sanitary sewers system. And sometimes we make allowance for it. That's what we call the inflow and infiltration allowance. We have a rate that we allow for, but as you will see, we never had I could not find through literature research and talking to people, any connection as to how these allowances have been derived, and whether or not any checks have been made that the way that we're operating the storm drainage truly affects the sanitary, the way the allowance in the sanitary has been defined. Typically, it's around 0.26 liters per second per hectare per area. 0.26, 0.3, 0.23, 0.2. There's a range, but it's typically between 0.2 to 0.3 liters per second per hectare that we use to size the sanitary sewer pipes. Okay, that's the wet weather response portion. There's a sewage portion when we're sizing sanitary sewers. Also, at least in Ontario and in a lot of parts of North America, we provide peak holes. And I'm going to use peak holes as one, not necessarily a defect, but it's the most obvious omission, I would say. I don't like to use that word because it is actually, they're needed. They have a function, peak holes. The name itself means that you use a pick, one of those machines, one of those tools that you make holes in the ground. But we also use those. I carry one in my truck all the time to open the lids. Okay, that's one of the functions. But we also use it for ventilation as well, especially in older days. Sewer systems, the construction wasn't controlled as well as it is now, and the slopes were not as accurate as they are now. And sometimes we had flat pipes, and sometimes we had sags in pipes that accumulated organic matter. And as soon as you accumulate organic matter and you take away oxygen, you get decomposition, and gas is the byproduct. You get hydrogen sulfide and you get methane. And so gas was a big concern, because methane, as you know, is an explosive. You get something that creates a spark, and the sewer system can blow up. And we have historical evidences and photos of exploding sewers. Not to mention that sometimes if you don't have your traps in your house filled with water, you're gonna get some of these gases into your home as well. And then the hydrogen sulfide is an odor, and it's highly toxic at higher concentrations as well. And those are byproducts of poor slopes, sewer slopes, and not enough flow as well to generate self-cleansing velocities. So there are things that were justified. Peak holes is one. The question whether or not you need one or two or multiple, that is a good question that we have some very strong opinions at our end, and we can share them one-on-one and so on, and we love to do that as well. But peak holes have a big role in this story because we're using them as our template for identifying and showing the extent of the problem between the interaction of the storm and sanitary sewer systems. The other point, which is a fact, is results from the standards, is the manhole densities. Okay, so the manhole density is basically how much water can enter sanitary sewers just based on numbers in a given area. So that is something that we are looking when we do this type of planning now and prioritizing how we can improve capacity in systems so that we can free up, solve basement flooding problems, solve environmental spill problems, solve lack of capacity for growth problems. This is one of the variables that have to be accounted for. How many holes you're allowing water to get into your sanitary sewer systems. And this is provable, this is observable, you can actually measure it, and I will talk about this as well. So there are some questions that we want to answer. We're not going to answer all of them in this webinar, Some of these answers need to be explained in more detail, and we will have some educational, more like classes that we would like to share with you guys so that we can go into more details. But I'm going to go through the questions and
I think Ed froze. Mariah, am I still good? Can you still hear me?
Yeah, you're good. I think he's frozen.
Okay. Well, I'll start going through, and then hopefully when Ed gets back, he can. I think he was having an internet issue earlier, so I will. Oh, okay, I'm good. All right, so just some of the questions we wanted to answer today, and or at least some of the questions we want to at least pose today, relate to how does I&I occur in some of the new development areas that we see. What constitutes an I&I defect, and as Ed was already mentioning, something like a pick hole was something that was engineered. It's not something that we would typically consider a defect. It's something that's always there and always has been there. So something that we need to answer there. Okay, Ed, you're back. I got through about half the questions. You're on mute. You're on mute, Ed.
okay, sorry about that, guys. I'm in the country. This never happened to me. I have really good reliable internet, but maybe today is a bad day. It's not too bad, but so anyways, I'm just going to speed up a bit just because of the time that we were losing through this. So one of the finger pointing is towards engineers and their supervision, and the contractors that are laying down pipes. They've been accused, I would say, not us. We don't get involved in the design and construction, but the industry in general has been pointing towards shoddy design, construction, supervision, and actual construction practices for high I&I in new development areas. There are defects, okay, in new development areas. We work all the time with municipalities finding and quantifying I&I in new developments, and we find defects. But I want to distinguish what is a defect versus what is part of the design or the standards that we are allowing this type of inflows into the system. Okay, I think we've been getting a bad rap, engineers and contractors, with new developments, with new construction. How do streets become storm channels? Okay, so again, I already mentioned this, that we use the streets as rivers. And I'm going to show you a sequence of graphs that I learned many years ago as part of the hydrology and hydraulic courses, and I did a little bit of teaching as well. But my first 10 years, I did a lot of what's called dual drainage analysis, and we'll show you some of those graphs in a few minutes. So I will also show what happens when a manhole lid, and specifically the two pick holes that I've been talking about, become submerged. And the other question is, can we predict which manholes are vulnerable to becoming submerged? Big difference in terms of inflows. If you get sheet flow reaching a manhole that is at grade, if there's no depression, because as soon as you have a depressed manhole, you're gonna get more inflows. But if you have sheet flow versus submergence, where the flow in the street is such that it is flowing but still submerges the lid by this much or by this much, as per the storm drainage design, what happens? And then what is the cumulative impact? If you have, this is not going to happen in every manhole because the grading design in a subdivision is different. So in some locations, you're going to get more submergence than in other locations. In some cases, you will just get sheet flow. As a minimum, you will get sheet flow. You get rain that falls on the lid, and some water will get in. And then the question is, can we gain capacity in a system by doing reasonable amount of work? In fact, we don't need to do too much field work to gain capacity. And I'll show you, I will quickly talk about this. But then how we do this is subject to more of a course that we want to offer to you guys. And what are other side effects? I mentioned gas, okay? Because maybe you're already thinking, oh, okay, so we're gonna seal a lot of manholes. But what about the gas that we've been talking about? Okay, so that's another point of discussion. So one of the key messages, sorry, can we go back to the
oh, sorry.
One of the key messages that I want to send is that the new solution to sewage capacity is not to go and start upgrading your system. It's not to go and build a bigger treatment plant because you've been having overflows, not to increase the pumping station, and not to go and replace or twin sanitary sewers. That may be the ultimate solution, but you should be looking at much easier fruits, lower hanging fruits to pick. And this is the key message that we want to send to you. This is something that you can do right now and gain a great return, measurable, quantifiable as well. So let's go to the next one. Okay, so I just want to go through the process of how runoff builds on the street. And why is this important? I'll show you this. So there are some terms that I want you to become familiar with. First of all, we have the gutters at the edge of the street, curb and gutter, and then we have the paved portion of the street that we drive on. There is a highest point on the street called the crown, and from the crown down to the gutter, we have a cross slope, a slope that goes down towards. We want the water to go to the edge of the street during normal storms and flow down the gutter until it encounters a catch basin, an inlet, a storm inlet. So I'm talking only about storm drainage. So there's a depth of flow on the street at any time when there's a storm. There's a spread which is measured from the curb towards the center of the road. There's a velocity that affects how much capacity that street has and how much capture occurs at the inlets and the grades. The grades have a capture curve that is characteristic of the shape and size and configuration of the metal grading. And we can talk, this is more, again, details I want to stay away from at this point. But the important thing is to know how much capture is happening from the surface into the storm sewers and how much is left over at the surface. If you don't capture it at the catch basin, which is, you can't, because during large storms, we don't design the catch basins to capture all this runoff. We usually want up to the 5-year here in Southern Ontario. And in fact, in many places in North America, it's 5 years. It's just that the size of the 5-year storm is different. In the US, Southern US, 5-year storm is way bigger than it is here. But there's going to be carryover past each inlet during larger storms. Let's go to the next one. So as the storm happens, you have the process where rain falls on the areas, it accumulates into the streets capture some of it into the storm sewer. So we have accumulation at the gutters. The gutters convey the water to the inlets go into the storm sewers, and so on. So we have a cascading effect. Let's go to the next one. So like I mentioned, the inlet grades, different types of inlet grades have different capture characteristics. This is one way that we can improve the blockage problem, is to change the grading and to select one grading that is less susceptible. We may think of making the holes a bit bigger. Okay, I don't know why we haven't thought of this, but maybe somebody loses their wedding ring, and they think it's the end of their lives, but maybe you can find it in the sump. I don't know. I'm just trying to be comical here, but one way to improve the fact that we're getting blockage and impacts to the sanitary often is because blockage leaves more water at the surface, and surface water creates a direct, not infiltration, inflow into the sanitary sewers, and you'll see. So this is just a sample catch basin capture curve that we use. Again, as the storm increases, we get more water along the gutters, but you see that there's a sanitary manhole lid that I'm showing here at the bottom right, that oval, dark oval. In that case, there's only what we call sheet flow, like low depth flow. It has a very localized tributary area. If that manhole, sanitary manhole, is depressed, everything that will reach it will go into the sanitary sewers. If it is fairly new construction, normally the lids and the gratings are at the same level as the surrounding asphalt. So some water will carry over towards the gutter. So key terms here are, again, we're introducing now sanitary manholes. There's going to be an offset elevation, and that's a key point, that the distance between the sanitary manhole away from the gutter will improve in terms of reducing the amount of submergence and the frequency of submergence. And our current standards already provide for that. They say maximum 1 to 1.5 meters away from the crown of the road. That doesn't always happen. In new subdivisions, sometimes it's hard to accommodate the utilities, and because of bends and conflicts, utility conflicts, we tend to sometimes to push the sanitary manholes closer to the gutters. Sometimes we find sanitary manholes right along the gutter, and we find pick holes, we find multiple pick holes, and those are really low-lying fruits that need to be picked off the tree before we start increasing the size of the pipes. I hope you can see that. There's no point of making the pipe bigger when you just have to fix the problem of one inlet allowing a lot of inflow into the sewer. So again, horizontal offset and vertical offsets as well. The higher the sanitary manhole lid, the better. Okay, let's go to the next one. So again, different types of sanitary manhole lids. Believe it or not, the top right, we found many of this in Toronto. You see this in combined sewers a lot. In combined sewers, you have perforated lids that into the combined sewer system because they carry stormwater too. But the problem is that some operators may just are opening several manholes in the vicinity, or whatever, for whatever reason, they end up putting these lids in separate sanitary sewer systems as well. And they become like catchbasing. They become like storm inlets into the sanitary sewers. Those are definite low-lying fruits. Okay, so some of the key elements in a sanitary manhole, there's a frame, which is where the lid sits on. There's a lip that extends away from the edges of the frame where this manhole sits. There's gaps, openings in that between the frame and the lid that allow inflows to get in. As soon as you have submergence, we see gushing water getting into those. Obviously, the pick holes, which is what we're using as our benchmark, how much inflow do they allow? There's other defects along the riser when you have cracks, and especially when they use brick and mortar. Older system use brick and mortar to raise and level the lids so that traffic will not go through bumps. Big defects can occur through there, and especially when you also have cracks around the manhole, like we're showing in one of the photos here. So those are defects, and I want to differentiate defects from design features such as pick holes. And again, depressed manholes, those are defects, I would say, too, as well. So this manholes are key. There's much more to talk about manholes. We live and breathe this stuff, so there's lots of stuff that we can talk about. Let's go to the next slide.
Probably have to speed up a little bit, Ed, just to
all right,
time check.
Again, so this just shows the pathways. Let's go to the next slide. Pathways that water gets from the surface into the sanitary sewers. This is the condition that we definitely need to avoid: submergence. Sheet flow you cannot avoid. You're still gonna get some sheet flow on top of manholes. Submergence, we cannot avoid it per se. You will have to have some manhole submergence. The question is, what do you do when you have manhole submergence? Do you seal the manhole? That's the obvious solution. But what about when you have consecutive manholes that you're predicting to be sealed? Do you seal them all? So what do you do with the gas? What do you do with maintenance as well? When you seal them, it just takes longer to do. Okay, so it might be one of the prices that we pay. So let's go to the next slide. So this is, I apologize for the graphic quality. I did this for another presentation just to show the maximum that we can allow on top of a manhole lid if we follow the storm drainage standards for a street. That in some cases we can allow 200 millimeters submergence in a manhole lid. So let's go to the next slide, because I want to show Okay, this is more or less shows the same thing with a standard street cross section. This is a residential typical single 2 lanes. There's 1 lane each way. Residential local street, and this shows a sanitary manhole, a meter and 1 meter actually. I'm not sure which municipality. We use many municipalities in Ontario to look at their standards. This is fairly typical. It's 1 meter away from the ground, which is good. We want to have these lids as high as possible. But you can see that if we follow the storm drainage standards, we're going to flood the lids significantly. In this case, it's close to 200 millimeters. It doesn't happen at every location, but it happens enough to create these inflows during large storms, which is what we're designing the sewers for. So again, photos here, this just show photos that we've taken during storms ourselves. Bottom right is again, in this case, the sanitary is closer to the gutter than the storm manhole. I'm not concerned about the storm manhole lids because the storm sewer capacity is much bigger, and you actually want to capture the storm water into the storm sewers, but not the sanitary. In this case, you see this was probably 100 millimeter depth, and water was gushing. And what do I mean by gushing? How does that compare in terms of the capacity of the pipe? We'll talk about this in a minute. So as I mentioned, when we design the sanitary sewers, we're designing them for critical conditions. We don't design them for days like today, or it's cloudy a bit. We don't design them for sunny days. We design them for a maximum of inflows that should be happening during a critical storm, large storm, 100-year storm. The system should be able to handle the inflows. So do we do that? That's the question. So for road drainage, the flow needs to remain in the right of way. We cannot allow the water to go into the private property. We cannot allow the water to go over reverse slope driveways, which I don't think they're typically allowed nowadays, but they are present all over the place because there's legacies, and some municipalities may still allow them. And if you do, you have to create a high point on the sidewalk or in the driveway to prevent water from the road getting to the basement. Anyways, the point is that depths on the road of 200 to 300 millimeters are acceptable as far as the storm drainage design is concerned. When we do that, we're submerging the entire road. The road becomes a river. Okay, typically operations, a lot of engineers think of sags, road sags, and yes, sags are typical vulnerable. You see them flooding all the time because inlets become blocked, and you get water, residual water, or the storm sewer is backing up and water will not drain. I have videos of residents kicking catch basins, raking catch basins and you can find them in YouTube, all kinds of videos of people just trying to clear the blockages. Let's go to the next slide. Okay, so I want to put some numbers. I want to put some meat in these bones now. So what happens when we allow the road to operate as per the road drainage design? What happens to the sanitary? And this basically, in simple terms, I'm using the orifice equation. If you're a civil engineer or environmental engineer, and you've taken some of the hydraulic courses, you will know you may be familiar with the orifice equation, which is the basic equation of how much flow gets through a hole if there's a certain amount of water sitting on top or on the side. It could be side hole or whatever, horizontal. There's different ways. In our case, these are the peak holes. I just did the peak holes. I did not account for any other inflow around due to cracks, due to gaps between the lids and the frames, none of that. I can tell you that on average, the actual inflow is about twice as much as what happens in peak holes. But I don't want to muddy the water, so to speak. I just want to use the peak holes. So these calculations show you that if we allow the maximum extent of flooding in the local street that I was just showing, which is typical, sometimes it's higher in some municipalities, sometimes it's a little bit lower, but very close. This is the type of inflows that we're going to get through 2 peak holes. 1.44 liters per second per manhole through 2 peak holes. Well, you may say, well, it's only 1.44 liters per second. The pipes are usually 40, 50, 60, 70, at least the 200, 250 millimeter pipes, depending on the slope, depending on the material. They have much more capacity than 1.44. Yeah, but that's just one manhole. There's no cumulative effects. There's no other defects. There's no dry weather flow. This is just one. So what does that mean? Okay, in terms of the design standard. So we can convert these 1.44 liters per second per manhole into liters per second per hectare as soon as we introduce the density of manholes that are present in an urban area. So very simple. We have all kinds of Google Maps, as simple as that. You can go and count the number of manholes, come up with an area, and you come up with a density. We have much more than that. We have GIS and all. So we come up with typical ranges of between 1.5 and 2.5 manholes per hectare. So if you multiply the maximum times the density, you get 2.88 liters per second per hectare. Okay. And I put in red, what is the standard that we use to size the sanitary sewer pipes? It's 0.26. It's more than 10 times less. We're getting 10 times more inflow from the two pickles alone. So some may argue, well, this doesn't happen in every manhole. True, I agree 100%. But in one manhole, we are exceeding over 10 times the capacity of the pipes because of the two pickles. Let's multiply the two pickles inflow times 2 because of other defects, gaps. Then that's 20 times the capacity of the pipe. Okay. And what's the cumulative effect if you have maybe not this amount, maybe 2 times the capacity of the pipe as inflow, 3 times? We have huge amounts of problems in the system. And that's why we are having a lot of problems in the system. That's one of the reasons. That doesn't mean that there are no other defects. There's no other I&I in the system. There is other I&I that we still need to continue the battle. But this is one clear victory that I believe, at least on paper, we have. We need to start sealing and doing strategic sealing. We have to do venting and measuring before and after to show solutions, problem solved in many areas. Let's go to the next slide.
So we got about 5-10 minutes, Ed. Just as
all right. Okay. Good. So this slide basically summarizes some of the variables that affect sanitary sewer submergence, because that's what we have to do. We don't have to go identify every manhole. That's easy to do, sanitary manhole. What we have to identify is the manholes that are vulnerable to submergence. Okay, we did a pilot already in York region. In the pilot area, which we selected a typical Southern Ontario subdivision, it was 20 years old, 25, so it's new. Okay, it's measuring a lot of I&I. York region has been breaking their heads. Why is this area responding? It was developed, Southern New Market, very new, relatively new, 20, 25 years. And they're measuring all these I&I in the system. So they're thinking there's supposed to be all kinds of defects, but they haven't accounted for these manhole inflows. Okay, so we did the pilot area analysis and we found that 10% of the manholes are the ones that are most susceptible to submergence. Doesn't mean that there are more, but the ones that will give you the biggest bang for the buck is about 10% in our pilot area. In your particular case, might be 15%, but out of 50 manholes, only 5 during the 100-year, 4 during the 5-year. We're recommending storm. These are storm return periods to seal, and we're going to be sealing them this coming spring. Okay, let's go to the next one. I don't want to go through all these details because of time. Again, I mentioned about blockage, inlet blockage. In the pilot area, I've been visiting this site every week, pretty much. I have photos of the same catch basins, and you won't believe and I'm not saying this is no reflection on operations. You cannot avoid this unless you actually go there every week and clear the grades. What we need to do is see how we can improve the grading, maybe doubling catch basins when you don't really need them. So I want to move on to the next. In one case, the bottom left photo there, you see the catch basin there. There's a catch basin there in that mud that I could not see it for several months because the debris was sitting there. Nobody was complaining. Municipal practice is maybe twice a year, if at least once a year, hopefully. They go in and clear this, but this is gonna leave more water at the surface during normal average storms. And if you have flow meters in your sanitary sewer system, you're gonna be measuring I&I downstream because water is reaching some of the manholes. Let's go to the next slide. Okay, so whenever you're doing this for land development purposes, so you have a developer that needs capacity in the system. We're doing this already in big areas in Newmarket. You need to demonstrate reductions in flow so that you can give half, what we call it the 2-to-1 ratio. Reduce two times the amount of inflow that's happening in one area, and you give 1 unit of capacity to the developer. They pay for it. They're more than happy to pay for it because doing this is way cheaper than, less costly than upgrading pipes, pumping stations, treatment plants, and the time that it takes to do all that. You need to do this to also to improve the treatment. Diluting water in the sanitary sewers during large storms shocks. It's not good for the bacteria in your treatment plants. So and not to mention the bypasses that you're likely causing through all this inflow. These are low-lying fruits to pick. Let's go to the next. Oh, so sorry. So I'm going to continue on the manhole flow test. Sorry, I have a couple more slides here. So these are some of our staff. We have several crews that can do this. We do it basically to quantify so that we can convert capacity reductions in a sewer by improving your infrastructure, the municipal infrastructure, in exchange for half the flow from new development. And that's new development without the I&I that is typically caused by this type of problems as well, because we are forcing, not forcing, but the new construction should follow practices that avoids this type of inflows as well. So in some areas, we use 3 times, 3-to-1 ratio. You reduce 3 times the flow for 1 unit of capacity. So let's Matt Malone actually has been running some of these developer-led I&I programs, and he can talk to you about more if you have any questions. Again, this just shows the impacts of the standards in several municipalities in Southern Ontario. We don't want to name them, but listen, we're all in the same boat. All municipalities have this issue. We hadn't found this connection until now between the storm and sanitary, the impact due to just peak holes. And this is not just in SAG areas, obvious low-lying areas, obvious locations where the sanitary is in the flow path in a ditch or on the gutter. These are manholes that seem to be okay. They just become submerged because the storm drainage, which is a relatively complex process because of imperviousness, because of spacing of catchbasing, because of blockage, it's hard to predict. But we have an analysis approach called an enhanced dual drainage analysis that we will train you if you're interested in a class setting. Okay, let's go to a next slide. So from our pilot, from the 5 manholes that we identified susceptible to submergence, we identified during the 25-year storm a 9.2 liter per second reduction in 30 hectares. This is a small subdivision, 30 hectare subdivision, 9 liters per second. That's it. When we start talking about cumulative effects, this is huge. In my 30-year plus career, this is credible that you can do this improvements by identifying and targeting vulnerable locations. And if you look at the seconds on the right-hand side of the table, it shows 12.8 liter per second reduction, or the peak flow that is being allowed during cases where the catch basins are 50% blocked. So the capture curve in the catch basins is only 50% effective, in other words. Okay, so you can convert these to volumes as well. So it's quantifiable. You can justify, and then you say, a developer, you do this, we're only going to give you 1/3 or 1/4 of this capacity, but you have to go do the work, pay for the work, get the work done, demonstrate it to me. I'm the owner as a municipality. I need to see the reductions. Flow monitor it as well. The problem with flow monitoring is that to demonstrate it, you need to have the flow meters longer because you have to do it. You have to capture it during large storm events. So this has to happen at least a couple times before and after, or at least once before and once after, to see a marked reduction. I'm gonna submit to you that you will see a reduction by sealing manholes pretty much right away, even during average storms because of blockage factors as well. Let's go to the next slide. Okay, I'm running this poll.
Yeah, this is just on. Sorry, this one is just to see. Now, this is the types of data when Ed was talking about performing some of this analysis, you know, when you want to identify some of this flood susceptible locations. So just a question sort of to the audience as to if you have some of this data in-house and sort of how comfortable and accurate you are in using some of that data in order to identify some of these locations. And maybe if you don't work for a municipality, this may not be totally applicable to you, but in terms of, do you have this information available so that you can perform some of these analyses to find some of these flood susceptible locations? So it looks like most people have sort of the asset data when it comes to, you know, your pipes, your maintenance holes, your catch basins. A lot have GIS data. Not so many are sure, I guess, on the LiDAR side of things, the ortho photos as well. So it looks like at least that asset data is there, which is a good starting point. And a lot of municipalities that we're working with are certainly either acquiring LiDAR data or they have the ability to acquire LiDAR data. So that's a good bit of feedback. So I'll just quickly move through conclusions because I think we're up against the time, but hopefully what we've presented today and what Ed's talked about a lot has shone a light on something that we think is a key issue and something that can help us in driving sort of I&I reduction into the future. I think we've highlighted that you know, at least in our minds, this impact of these standards and the stormwater on the streets, the impact on the sanitary system is maybe a little more significant than we previously imagined. You know, as Ed mentioned a couple of times, these are what we think are sort of low-hanging fruit that can be easily identified and prioritized. We can quantify how much flow is getting in through these types of you know, we'll call them defects, really they're not, but you know, through these maintenance holes that are susceptible to flooding. These are applicable again to existing areas, older subdivisions, as well as new subdivisions where there may be some I&I concerns. And really we see this as a problem. It's not, you know, it's not finger pointing. We want to bring it to the light and really applies to not just only Ontario, but you know, Canada, US, Europe, wherever the standards are allowing for these, you know, essentially the streets to act as river channels, as Ed mentioned. So what's next? So, you know, Ed's been working with the MECP to update the provincial drainage standards, at least for new developments. Again, it's going to be tough to go back and fix a lot of it for the older areas, but you know, the guidelines, the standards, you know, should be updated. You know, we are developing tools. So a bit of a teaser for some of our upcoming webinars is developing these tools to identify these locations where these maintenance holes may be susceptible to flooding, doing manhole flood tests and quantifying how much is getting into the system. So we have these training or webinars that you know, feel free to reach out and we can certainly facilitate for yourself, for everybody out there, and just a number of, you know, sort of solutions that that may pose and allow you to capitalize on. So just one last poll, and hopefully if you're able to stick around, that'd be great. Just if you're interested in, you know, working with us one-on-one, if you want to talk about how this may be applied in your particular jurisdiction, or you know, if there's those solutions that you want to talk about, or if you want to learn more, then, you know, by all means, feel free to reach out. We'll just give that on a few more seconds. Okay, so again, thanks everybody for coming. I did see a question in the Q&A, and I'll try and get to that in a second. Just, you know, a heads up on the upcoming webinar and training that we're doing, which currently we have one scheduled for February of next year. But with that, thank you very much for coming, and hopefully you all have a wonderful holiday season. So thank you very much. There was a question just around and Ed, I know we've run into these a few times before, just along the rain dishes or the inflow dishes that some municipalities have put into the sanitary manholes to help alleviate some of these issues. So I just said, sometimes those can be, I've seen it in a couple situations where they're removed, or they're, somebody smashed it down into the maintenance hole. So there's a little bit of an operational concern that I've seen with using those inflow dishes. I think they do, in my experience anyways, they have worked effectively in some locations, but there are other options, and we can talk about that next time as well, as to what some of the options may be when it comes to sealing or trying to mitigate some of these flows. I don't know if you want to add any more on that as well. Or if you froze.
Yeah,
I think you might have froze. So there's another question. Sanitary manhole lids that are closed type, is inflow an issue with those? I guess it depends on what you mean by closed types. So there are some that have no pick holes, or they have the hooks, or maybe very few openings that the water can get through. It depends, I guess, on again, as Ed was mentioning, that we've identified through some of the testing that we've done, is that the gap between the cover and the frame, if it's not fully sealed, if it's not one of the maintenance holes that are cranked down with a gasket, that some of the water can get through between the frame and the cover. And then if there are any defects or cracks or gaps between the frame and the road, or cracks in the road that allow water to sort of penetrate against the frame or the chimney of that structure, then it would still allow some water in. So it depends on sort of site specific conditions, and that's why we go out there and do a lot of that flood testing as well, to see what's happening at particular locations where we can do that type of testing. So just in terms of statistical data about manhole flooding under design, did you look at statistical data about manhole flooding under design storm conditions? If such a data is available, it could further help to implement tailored solutions for vulnerable areas. So I think that really speaks to what we're doing in our probably follow-up session, or if you want to do a session with us, we'll be looking at some of those techniques about where, how we analyze and model where these locations will be that will be more susceptible to flooding under, again, certain design conditions or design storm conditions. So that's something that we're actively looking into. We've done some work in it, and will be again part of our future presentation and our training that we look to set up with you. Yeah, there's a question about whether the problem is accentuated by winter weather, when catch basins may be iced over or snow is piling up. Yeah, I know Ed's he talked about going out to the site, and he's done some of that work also in the winter, and yeah, exactly that. There's been cases where the catch basins are blocked by snow, other debris, ice, and yes, it certainly accentuates the problem in that case. So yeah, it's certainly something that we've identified. We've been focusing mostly on, even just during, as Ed mentioned, these sort of what is it? It's ideal conditions, right? We're still running into these issues. So if you talk about debris blockage, as Ed showed the pictures of the mud or anything like ice or snow, certainly it's going to make the problem even worse. So yeah, a very good point, and a good question there.
I just want to add, Matt, that I don't know who asked that question, but January 10th to 11th, 2020. Big problems in some of the municipalities in the GTA. I have photos of similar conditions at other times, but there was a snow melt plus rain event on top. It was mostly a rain plus melt in an area where the snow banks at the edge of the roads had been left away from the curb. Like, I don't know if you know this, the snow removal practices don't always remove the snow right to the curb. They leave a portion because the width of the street only allows certain width. The width of the snow blades only allows certain amount, and they want to get through certain areas, and so they don't cover the entire street and they don't go all the way to the curb. So they leave a portion. In this case, in many areas, they left about a foot away, a foot and a half away from the curb, filled with the snow bank was part of that. And through snow melt and refreeze, melt and freeze cycles, there was a cake snow ice layer on top of the catch basins. And then we had this event that it was rain event in January 10th to 11th that created all kinds of surface flooding on streets and in receiving water courses as well, because snow and ice had come together to create dams all over the place and blockages. So this is a very common problem that happens when we don't clear the snow right to the curb. And like I said, in some cases we may not be able to, but then we have to at least be selective where we allow it and where we don't allow it, just based on knowing which areas are more vulnerable to submergence, manhole submergence.
There's another comment about not sealing manholes due to methane gas or any sort of gas buildup, and I think Ed talked a little bit about that earlier. And we've done, we have sealed a few manholes, and we've done a few gas studies just to make sure that there were similar concerns where we were working, and so we were able to monitor in the maintenance hole that we sealed, as well as upstream and downstream, and identified that there were no differences and there was no buildup of gas in the particular one that we sealed. But it is something that certainly needs to be taken into consideration. And I know Ed's been pretty adamant that as long as you have good hydraulics and good flowing sewage and water through the system, then really that's pulling the air with the flow, right? It's allowing some ventilation even in of itself. So we're typically, when we do this type of analysis, we're not recommending that a whole subdivision, all of the maintenance holes are being sealed. It's usually just these sort of flood vulnerable locations. And as we've seen in our studies, 10-15% of the maintenance holes in a given area. So we still feel that there's quite a bit of ventilation that's happening from these other locations that aren't being sealed. But it is something, again, that does need to be taken into consideration when we propose something like this. We go in, make sure when we look down that there is good hydraulics, there's good, constantly flowing water or sewage, so that we can make sure that we're not proposing locations where there may be gas buildup. That, if there are situations where gas is a concern, I mean, there's goosenecks, there's things like that we can install to help with that ventilation as well. So there's some ways around it in terms of, both mitigating or looking at those risk factors, and then, installing or doing certain things to make sure that the gas isn't a concern. And then the last question, what sort of modification do you recommend to utilize maintenance hole capacity to a desirable level? What sort of, I'm not sure I quite understand that one. Maybe Ed, do you want to take the go?
Yeah, that's a good question. Okay, so how far to take this, in other words? First of all, if you have problems right now with capacity, yeah, you need to start looking at this right away. If you're thinking of expanding, you have a development pressure like a lot of the GTA has, and a lot of it is vertical, where you go into a high rise where that it's adding more dry weather flow. You need to verify the capacity downstream, and if you already have problems in that area, definitely start looking at on a sewer shed basis. So you can focus your efforts in areas that need the benefits of flow reductions. If it's the treatment plant, it's going to be the entire area upstream of the treatment plant. But even that, you can prioritize it to where the response is the highest, and you can find the lowest hanging fruits. You can get the biggest benefit in terms of freeing capacity by eliminating inflows in the areas that are generating the most inflows. And for that, we do flow monitoring. So we, not just at the plant, but we divide the plant tributary area into sub sewer sheds. And then we break down the sub sewer sheds that are generating the most I&I rates into further areas, so we can begin to isolate the areas that need the most attention. So operation and maintenance can focus in a rational prioritized manner, the areas that you can achieve the biggest results the fastest. And like I said, developers are more than happy to fork out the cost of doing this. We're working with several to do this in York region, because they already have a program. We started with pilots doing this, so they said, well, we're not convinced that it's going to work. 2 or 3 years ago, they converted the pilots to a program now. It's full time. So if you're in York region, we can do this. I mean, Markham, anywhere where you have local capacity problems, it doesn't have to be regional. The York region was motivated because of regional sewer capacity issues, but this also happens in the local trunks before they go into the bigger trunks as well. And if you're a single tier municipality, there's no such thing as regional or local. Everything is under the same jurisdiction. So there's a rational way to do it. If you have low budget, you start with a pilot area, and then you can look at the results of doing this work, and then you can expand it accordingly as well based on results.
Awesome. Well, thanks everybody for sticking around, and if you have questions, we'll be more than happy to stay. But yeah, I think we're a little over time. So again, thanks to everybody for coming.